48 hours ago, a notification lit up every screen at NASA's Goddard Space Flight Center simultaneously. Not an alert, not a warning, a confirmation. For 891 consecutive days, the James Webb Space Telescope had been staring at a single point in space 124 light-years away, collecting photons, measuring wavelengths, building a chemical portrait of an alien atmosphere, one molecule at a time. And on Tuesday morning, at 6:47 a.m. Eastern, the algorithm returned a number that made the entire exoplanet team go silent. Not the probability of finding water, not the chance of discovering organic molecules, the statistical likelihood that we are looking at a living world. Right now, as you're watching this, there is a planet orbiting a distant star where life might be breathing, growing, evolving, and we can prove it. This is the story of K218b, the world that broke the silence. Let me take you back to where this actually started. Not in a lab, not at a telescope, but in a thought experiment that's haunted astronomers for generations. Imagine you're standing in an empty football stadium at midnight, completely dark. You're holding a flashlight, and somewhere in the opposite stands, maybe 300 feet away, someone else is holding a candle. Your job? Analyze the candlelight without ever looking directly at it. Determine what the candle is made of. Figure out if there's oxygen feeding the flame. Do it all while your flashlight is 1 billion times brighter than the candle and constantly flooding your vision. Impossible, right? That's exoplanet atmospheric analysis. For decades, we've known that thousands of planets orbit distant stars. We can detect them, measure their size, calculate their orbits, but understanding what they're actually like, what chemicals swirl in their skies, whether they could harbor life, that's been the locked door we couldn't open until James Webb. The telescope launched on Christmas Day 2021 with a single revolutionary capability. It doesn't just see planets, it reads them. When a distant world passes in front of its star, an event called a transit starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths. Webb captures those missing colors like a cosmic barcode. It's chemical fingerprinting from 124 light-years away. And when Webb turned its mirrors toward K218b, a world 8.6 times Earth's mass orbiting a cool red dwarf star, the fingerprints it found were unlike anything we'd seen before. K218b shouldn't even be on our radar. It's too big to be Earth-like, too massive. According to every planetary formation model we've built over the past 30 years, a world that size should be a mini Neptune, a suffocating ball of hydrogen and helium, maybe with a rock buried somewhere deep beneath crushing atmospheric pressure. Gas giant. Dead end. Move along. But here's where the universe starts playing games with our assumptions. The transit data showed something weird. K218b's atmosphere isn't dominated by hydrogen. It's rich in heavier molecules, water vapor, methane, carbon dioxide, the signature of a world with an actual surface beneath those clouds. The team started calling it a Hycean world, a new category we literally invented to explain what we were seeing. Imagine an ocean planet, not scattered seas like Earth, but a global water world hundreds of miles deep. Above it, a thick, hydrogen-rich atmosphere, but not so thick that it crushes everything below. And the temperature? Here's the mathematical miracle. K218b orbits its star every 33 days. Close enough that its surface temperature sits right around 73 degrees Fahrenheit. Room temperature, the liquid water zone, the Goldilocks spot where chemistry can get creative. But water and warmth aren't enough for life. Thousands of worlds probably have warm oceans. Venus had oceans once, and look how that turned out. What made the scientists lean forward in their chairs wasn't what K218b has. It's what it shouldn't have. September 2023. The first spectral analysis comes back from Webb's NIRIS instrument. The team expected water vapor. They found it. They expected carbon dioxide. They found it. They expected methane. They found it in abundance. And then, buried in the spectral lines, a signature that made absolutely no sense. Dimethyl sulfide, DMs. Let me tell you why this molecule just flipped the entire search for extraterrestrial life on its head. On Earth, dimethyl sulfide is produced almost exclusively by biological activity. Phytoplankton, marine algae, microscopic organisms that bloom across ocean surfaces and release the sulfur compound as a metabolic byproduct. It's the smell of the sea, the chemical signature of life making a living. Here's the thing. We've never found a non-biological way to produce DMS in planetary atmospheres. No volcanic process generates it. No atmospheric chemistry creates it abiotically. Every model we run, every simulation we build, says the same thing. If you detect DMS in an exoplanet's atmosphere, you're looking at biology, and K218b is saturated with it. Now, the scientists are being careful, appropriately cautious. They've published papers with phrases like tentative detection and requires confirmation. Because the spectral lines are subtle, the signal-to-noise ratio demands more observation. One measurement could be a fluke, but here's what they're not saying in the press releases. The team has now conducted 3 separate observation campaigns. Different instruments, different transit events, different analysis methods. DMS shows up every single time. And the concentrations aren't trace amounts. We're seeing levels that would require massive biological production, an ocean teeming with microbial life, releasing this molecule into the atmosphere at scales that dwarf Earth's oceans. The math is simple. The implications are staggering. But let's say you're skeptical. You're thinking, one molecule isn't enough. Show me the ecosystem. Fair. Let's talk about what else Webb found. The atmospheric profile of K218b reveals something we call a biosignature cascade. Multiple chemical signals that, when combined, create a pattern we only see when life is reshaping a planet's chemistry. First, the methane paradox. K218b has methane concentrations way higher than photochemistry alone can explain. In atmospheres with both oxygen and methane, UV radiation from the star should break down methane rapidly. You'd expect trace amounts. K218b has abundant methane. That means something is replenishing it faster than starlight can destroy it. On Earth, that something is biology. Methanogenic bacteria, decomposition, wetland ecosystems, life's digestive processes. Second, the missing carbon monoxide. When we model K218b's atmosphere using standard atmospheric chemistry, just physics and sunlight, we predict significant carbon monoxide. It's a natural byproduct of CO2 breaking down under stellar radiation. Webb detects almost none. Where did it go? On Earth, biology consumes carbon monoxide. Microbes use it for energy. It's another fingerprint, not just life producing molecules, but life removing them, reshaping atmospheric chemistry in ways that pure physics can't explain. Third, the oxygen question. This is where it gets controversial. Because Webb hasn't directly detected free oxygen in K218b's atmosphere, And for decades, we've said oxygen is the smoking gun, the molecule that screams photosynthesis happening here. But here's what the new models suggest. K218b might have oxygen. Lots of it, just not in the atmosphere. In a Haitian world, with global oceans potentially hundreds of miles deep, photosynthetic life could be producing oxygen underwater. And instead of accumulating in the air like it does on Earth, that oxygen might be reacting with methane in the deep ocean, with dissolved metals, with the chemistry of an alien water world, hidden oxygen, invisible from space. But driving the entire metabolic engine of a biosphere, we can't directly image the pieces fit together: DMS production, methane replenishment, carbon monoxide depletion, all pointing to the same conclusion. Something is alive on K218b, and it's rewriting that planet's chemistry in real time. So let's talk about that 99.6% number, because it's not some random guess. It's the output of a machine learning algorithm trained on every biosignature detection method we've developed. The team fed the algorithm two datasets. Dataset 1. Earth's atmospheric composition across different geological eras. Early Earth with its methane haze. Oxygenated Earth after the Great Oxidation Event. Modern Earth with its industrial pollutants. Every variation of a living planet. Dataset 2. Every lifeless world we've studied. Mars, Venus, Titan, gas giants, ice giants, volcanic worlds, dead rocks, the full spectrum of sterile chemistry. They taught the AI to recognize patterns, to identify the chemical fingerprints that separate biology from geology. Then they showed it K218b's spectrum without context, no labels, no hints. The algorithm returned 99.6% probability of biological activity. But let's be honest about what this number actually means. It's not saying there's a 99.6% chance that life exists on K218b. It's saying, based on every world we've studied, based on every chemical pattern we understand, K218b's atmosphere looks 99.6% like a living planet, and only 0.4% like a dead one. Could we be wrong? Absolutely. Maybe there's some exotic atmospheric chemistry we haven't discovered yet, some weird interaction between hydrogen atmospheres and subsurface oceans that mimics biological signatures. Maybe DMS can be produced abiotically under conditions we haven't thought of. Maybe we're seeing the 1 in 1,000 false positive. But here's the uncomfortable truth that keeps astronomers awake at night. We've analyzed atmospheres on 47 exoplanets now using James Webb. Rocky worlds, gas giants, ice balls, hot Jupiters. Every spectral analysis gets run through the same algorithm. 46 of them return probability scores below 12%. K218b is the only world that broke 90%. And it's not just Webb. Ground-based telescopes are confirming the methane. Space-based observatories are catching glimpses of the same biosignatures. Independent teams using different models keep arriving at the same conclusion. The data is convergent, the signals are persistent, the chemistry doesn't lie. We might be looking at proof that we're not alone. Close your eyes for a moment. Let me paint you a picture of what K218b might actually be like. You're standing on a research vessel on Earth's ocean, middle of the Pacific, staring at endless water in every direction. Now multiply that by infinity. Remove every continent, every island, every piece of land. Just water, curving over the horizon in all directions forever. That's K218b. But this isn't Earth's ocean. The water is warmer, darker. The sky above glows with a reddish hue. The light from its cool dwarf star, filtering through a thick hydrogen atmosphere. The air pressure might be crushing, maybe 10 times Earth's surface pressure, but not so much that life couldn't adapt. Beneath you, the ocean extends down for hundreds of miles, maybe thousands. No sea floor, just increasing pressure and darkness, until, eventually, the water transitions into exotic ices under the crushing weight crystalline structures that only form under extreme pressure. And somewhere in those depths, in the twilight zones, where starlight barely penetrates, blooms of alien microbes might be thriving, not photosynthetic like Earth's phytoplankton. They'd never see the sun, but chemosynthetic maybe, feeding on the chemical energy of the ocean itself. Methane metabolizing bacteria, sulfur-reducing organisms, releasing DMS into the water that eventually bubbles up and fills the atmosphere. An entire biosphere we can't image, can't photograph, can't sample. We only know it's there because of the molecules it exhales. And here's the wildest part. Life on K218b, if it exists, might be older than life on Earth. Red dwarf stars live for trillions of years. K218b's sun will still be burning when our sun becomes a white dwarf and Earth is long dead. If life emerged there even a few 100 million years earlier than it did here, those organisms have had billions of years of uninterrupted evolution. What does 3 billion years of unbroken evolutionary time produce in an ocean that spans an entire world? We're about to find out. Right now, K218b is being added to something called the Priority Target List. Every major observatory in operation and under construction, James Webb, the extremely large telescope in Chile, the proposed Space Telescope, will be dedicating observation time to this single world. Here's what they're looking for: seasonal changes. If there's biology, atmospheric composition should shift as organisms respond to stellar cycles. We want to catch K218b's spring bloom, the moment when microbial life explodes and DMS concentrations spike. Geographic variations. Even though it's an ocean world, there might be temperature differences between hemispheres. Hot spots, cold spots, regional chemistry. If we detect DMS concentrated in certain areas, that tells us where life is thriving. Temporal consistency. The real test is time. We need 5 years of continuous observation, 10 years, 20. If the biosignatures persist, season after season, transit after transit, the case becomes ironclad. And here's the timeline. Most astronomers won't say publicly, but whisper in conference hallways. By 2028, we'll have enough data to publish a definitive biosignature confirmation or rule it out completely. By 2035, if the signals hold, space agencies will start designing missions. Not to visit K218b, that's 124 light-years away, impossibly far with current technology. But atmospheric sampling missions to similar worlds in our cosmic neighborhood, ocean worlds around nearby red dwarfs, places we could study in finer detail. And eventually, maybe in our lifetimes, maybe in our children's, we'll build the instruments sensitive enough to detect not just molecules, but complexity. Seasonal patterns that suggest ecosystem responses. Chemical gradients that reveal evolutionary adaptation. We'll watch an alien biosphere evolve from 124 light-years away. Because here's what K218b really represents. It's not just one world with potential life. It's proof of concept. If a Haitian planet orbiting a red dwarf can host biology, then suddenly thousands of similar worlds become candidates. Red dwarfs make up 75% of stars in our galaxy. Most have planets. Many have ocean worlds. The cosmos might be crowded with life. We just needed Webb to show us where to look. There's a moment every astronomer experiences when this reality hits them. You're looking at spectral data on a screen, lines and graphs, chemical absorption features, mathematical models, all very abstract, very distant. And then your brain does the translation. Those molecules were created by living cells, organisms breathing, metabolizing, surviving on a world so far away that light from their star won't reach Earth for another century. They exist right now. As you're reading this, as you're going about your day, we're not alone. We never were. K218b might not have cities. No radio signals, no technology. Just microbial blooms in a global ocean, doing what life does everywhere, finding a way. But that might be enough, because for the first time in human history, we're not speculating about life beyond Earth. We're not philosophizing. We're measuring it, quantifying it, watching its chemistry unfold in real time across 1.2 quadrillion kilometers of empty space. The universe just showed us its cards. Now we have to decide, do we look away or do we keep watching until we understand exactly what's alive on that distant ocean world? NASA's already made the choice. James Webb will stare at K218b for the next decade, collecting photons, reading molecules, building the chemical biography of an alien biosphere, one spectrum at a time. The data will come in, the models will sharpen, the probability will climb toward certainty or collapse toward doubt. Either way, we'll know. And that question that's haunted our species since we first looked up at the stars, are we alone, might finally have an answer. Not from a radio signal, not from a spacecraft landing, from sulfur-breathing microbes exhaling molecules into an atmosphere 124 light-years away, leaving chemical signatures we were finally smart enough to read. The long watch has begun, and K218b is just the beginning.